Let's see if we can take the hardest stuff of physics, the quantum gravity, and distill it down to the easiest possible thing, just basic geometry. Well, first let's start with this whole t squared, x squared, y squared, z squared. This is just the regular old space-time coordinates we use, time and space. Pretty simple. But we realized something strange. You think about like the Pythagorean theorem, like a squared plus b squared equals c squared. We live in a squared world. We live in a world where there's like square invariance, where like you start plugging things in and it doesn't matter which direction you're in, you're always measuring like the same quantity. That's the invariant part. Well, what if we started to factor this? So we start factoring this out and we can get these little factors like t plus or minus z and then x plus or minus iy. You factor this out and you basically just get the same thing. So you can get these weird little linear factors. These are just linears, yeah? But if we're looking at just position space, that's not really super helpful for like quantum physics or physics stuff because position is kind of cool, but we care more about momentum and waves. If we want to do wave stuff, we have to go into waveform. So we're gonna have a look at momentums, and all we got to do is convert, you know, uh, the time to energy, and then we convert the position to momentum, and then we're just gonna map everything across. Okay, so just slightly more complicated. We're in energy and position and momentum space rather than in position space. But it's the same idea. Okay, so we're just factoring these things out into linear factors. Now we basically rebuilt space-time out of these factors, these linear factors. Now what we should be able to do is if we want to be able to like build the particles, we have to take some square roots. So the quantum world happens in the square root world. And you get the square root spinors, these spinor roots. And all it is basically, let's just consider this for now. We have the positive energy and the positive version of the momentum. That's just going to be E plus or minus and E plus or minus. And yeah, we're just mixing energy and momentum here. So we're just kind of uh, flipping these things, and it's basically just taking a square root of our factors. So now we multiply them together. If you did that, then you'd get back to your original factor. So it's kind of crazy, but all we're doing is we're just square rooting stuff over and over again twice. Or we could square it twice. But as you start to factor these things out, you get all these different combinations and possibilities, right? Yeah, I know this looks a little bit weird, but these are the original ones. And you see that there's like a square root of the e there. If you multiply this whole thing by square root of e, then what happens is you get a simpler version. So kind of just a little bit of just try to keep things super, super, super simple to the point where it's just pretty much uh, uh, it's just it's just easy peasy, lemon squeezy. All right, now let's take a look at these weird derivatives that we're doing here. This is where it kind of gets a little weird. But, but, all we need to do is realize that we're in three spatial dimensions, right? This thing X, this thing Y, and this thing Z. So what if we started to twist these up? Twist it up. And if we twist one of those up, and twist the little strand up, we get a single helix, a little helix. That's that's this little thing right here. It's a U1 helix. We're just twisting up a strand of spacetime, one of the dimensions. And we can do that with two. We can combine two of them together. And if you do that, then now you're starting to mix things. So now we're moving to level two here, SU2. We got a double helix wrapping around. We just got like energy and momentum sort of switching back and forth. You can see how they can sort of choose between being in the energy position or in the momentum state. And then, and we can also twist this up into a triple helix over here. This is a SU3. Now we have to sort of introduce a new Q dimension. So the Q dimension is actually the same as the momentum. It's just you're mixing Y and Z momentum versus X and Y momentum. But you could also choose any. So these are all like kind of like there's one particular factor, but obviously you could sort of keep factoring these out in different ways. That's why quantum mechanics is written in this really generic form. This is all like super generic. and I'm picking one possible combination. And to make it simpler, because that one combination just comes out to be E's and P's, so energy, momentum, makes sense. If you start doing the general case where you start looking at all the possible combinations, you have to use a different letter here now. Well, they like to use, physicists like to use these crazy letters, so like the W boson, the B boson, these fields, and you got these generators and stuff. Let's not worry too much about that. Let's go back to our helixes. All right. Now, what's weird is if you have a double helix, you can twist up two of your strands and you have one loose. Yeah. And then if you have the three helix rule, we'll just consider that you're confined to the space of three helix, a triple helix. So you're confined to the space of a triple helix, and within that you can flip two of them, and you still got one to rotate. So this is the idea of the standard model, is literally just have a triple helix, and then you could take two of them and flip them around, and then you still got one left. And then that's it. That's the whole standard model. This is all quantum mechanics really is. Boson quantum mechanics, that means. This is just bosons right here. We haven't gone to the fermions yet, but they just pop out immediately. Immediately. So let's not worry too much about that. All right, remember, we're trying to keep things super, super, super easy here, okay? All we did was we took our t, x, y, z's, converted it into a little matrix right here, 2 by 2 matrix with our factors, little cross factors. We simplified it to t plus t minus x plus s minus. We don't have to think too much about all that. And then we translated it into energy momentum space so we can work with waves. And then we started twisting dimensions up. You can get these little strands. Okay? Um, so let's work with the first strand right here. This first helix. This is the U1. This is just basically you're multiplying whatever number you get by 1. So you just multiply by 1, multiply by 1, multiply by 1. That's all that U1 is doing, multiply by 1. You could do that with the energy dimension, you could do that with the P dimension, you could do that with the Q dimension. When you multiply by 1, though, you're kind of rotating. So, whatever. Let's look more at 2, because this is where it starts to make sense. You can see how we kind of have to like switch sides, and there's 3 different ways that we can do that. The generators, T1, T2, T3. So far, we're just basically building up a 2-dimensional space, and we can pick directions. You can look in this direction, or this direction. Those are the 3 different ways we could represent a 2-dimensional space. But we need to have currents. We need to give these ones and zeros physical value. So we multiply it by this. We've basically just taken our first piece, which is P1 over here. There's the negative, and then we have the positive P right here. And that's basically all we did, was just mapped it from here to here, and we transferred across, multiply it by G. This is the second G because we're in the second tier here, double helix. We get the second G. Back to the first one, you see this is just G1, and well, this is just the remaining factor after we've taken up these. You get this one left over. Um, so these are just different ways that we could factor this. And these are generators, these are currents, and the crazy thing is that we have these bosons, and the bosons are combinations of these generators. Um, so, you got the W plus minus boson, you got the Z boson, and you have the photon, which is this one here. It's the photon. Uh, yeah, photon. I don't know where I write them, but you get the W bosons. This is the weak bosons. Um, and then again, you have kind of the photon for light. All right, so we've popped out our bosons, and we can sort of plug them into the Lagrangian over here. See the Lagrangian. This is just kind of generalizing it again and combining them so we could take the Lagrangian and figure out the energy and all the complicated stuff that comes with it. But and here's how we can take the derivative and see that we have the bosons kind of combining together like this as well. We have to multiply the boson by the generator, so that way we kind of couple them together. So we build this little this little directional position, choosing ones and zeros, okay? And then we give it some physical meaning here. That's kind of giving them like well, this is basically the street, and I guess these are the signs that are actually on the street, so you know what street you're like going on, names on the street. And then if you want to have a car, you're gonna have a boson, so you have to drive your car, and you're gonna go down street left and right, and then you got a boson. And like bosons just make little loops and stuff, so they kind of combine. You got like taxis and like stuff like that driving around. They had like two passengers on right there. So we're just combining stuff here. These ones combine the blues right here, and the T3. I think this is T3. I'm not exactly too sure, but it gets a little bit complicated with all these indices and stuff. You can see it's pretty simple if we just factor it out. We get down to the ones, the p's, and e's, the charges and the currents, and now let's go to level 3 before we head on to the most important part, which is how do the particles pop out? Because we just have bosons here. But we can see if we want to get gluons, we're gonna need 8 generators over here, and all the 8 generators just go to one particular gluon. The reason is because we don't have to mix anything anymore. We're just loose, kind of in the three-dimensional space that kind of already mixes everything together in this one thing. So we don't have to do any kind of superpositions. Already got all the combinations here. So this gives us our 8 generators, our 8 gluons. And of course, when we're considering the easy version, or the version that makes sense is like energy momentum in different directions. But if you want to call it colors, you can also call it colors. Okay, you got red, green, and blue, but it's technically just measuring energy and momentum in different directions. So technically this is correct and this is a little bit heuristic. But that's really besides the point, I guess. Hopefully we can understand now how the standard model and why particles even exist and how they're put together. All we're doing is we're putting helixes together. But we're not done yet because remember we have to close these things with rules. We have to have strict rules to close these because we can have any kind of combinations of things and there's very specific reasons why fermions pop out. Because we have to close the helixes with rules and and consider the triangle anomalies. So let's go back to here. This is just kind of a review because we closed the helixes last time. But here's the helix closing. So we got 3 dimensions. So what we kind of want to be able to do is use the U1. This is it's kind of like a photon, but basically we're using the most fundamental unit to close the helixes. So you could take pairs from the other 2 dimensions. So let's take the U1, U1, and we got those 2 strands wobbling together, and we just gotta close it up, and finish it up, finish the helix loops, and get to 2 pi again. We want a full circle, so that's the key, is we have to finish that 2 pi loop. 2 pi, 2 pi, 2 pi. How do we close these things with 3 helixes? You have to have a multiple. We'll come back to that. But anyway, so let's go back to this. We also have SU2, SU2. These are the pairs of SU2s coming together. Double helixes are approaching each other. We need to close it with a U1 because it's the most like fundamental unit. It's like think of the U1 as the zipper. We're just zipping things up. And you have the stuff on the sides that kind of zipping together, right? You could do that with SU3. So you got these triple helixes, and you got the U1 zipping them together. This is pretty simple stuff. And finally, you have the graviton. This is actually the spin, 4-dimensional stuff. So it's a little bit more math involved. But these things also come together, and you bind them together. So by getting these rules and by closing the helixes with these triangle anomalies, then we can actually quantize all the charges of the lepton of the fermions. So, this is just Feynman diagrams and the triangle anomalies, but we can see why it even happens because we're closing helixes. The helixes must uh, reach 2 pi closure. And what do I mean by that? Let's return back to this again. We have a single helix going 2 pi, you divide that by 1, a double helix 2 pi over 6, and a triple helix 2 pi over 3. So what's the least common denominator when you have a 1, 2, and a 3 on the bottom? The least common denominator is 6. So you start dividing things by, you divide the circle by 6, and all of a sudden you get pi over 3. And then you start quantizing all of your stuff by pi over 3, and you start to sort of add those together. Of course, that results in infinite combinations. So that's why we need to close them with the other helixes here. So you got, for example, here, what we're doing is we're taking our 2 pi over 2, so we're left with a pi. So what we needed to do is we multiply 3 by the pi over 3. So this is the least common multiple. We have 3 times pi over 3, we return to pi, and then we just multiply it by 2 again. So essentially you get 6 times pi over 3 again, returned to 2 pi. Here you do that with the triple helix. Again, you sort of take your 2 pi over 3, you take 3 of those. It gets you back to 2 pi, but you also take 2 times pi over 3, and then you have 3 of those. So you can just split these things up. But the point is that the only one that takes the smallest unit is U1. This is the only one that has the power to close things, is U1. Because these ones are taking bigger steps, so they can't close themselves completely. The only thing that can finalize the close is the U1. And that's why we choose U1 to close these things. Boom, 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 boom. We zip them all up, and now we close the triangle anomalies. And we can sum it all up like this and make a little bit of a complicated mess. And then we can derive our little standard model. You can see how geometrically it makes so much more sense to derive this geometrically than it does with like all this stuff that kind of doesn't really make too much sense unless you kind of can see it geometrically, and then it starts to make a little bit of sense. So, I don't know, it's kind of interesting. But this gives the charges to all the fermions. You can see we sort of had to get exact y's for them. The 1/3, 1/3, 4/3, -2/3, -1, -1, -2, 0. And if we do that, then we no longer have infinite combos. They break down to specifically only these survivors, which are the 6 fermions. Whoa. Okay, so that's pretty cool. And finally, one last thing before we head out of here. One last thing is that we'd like to be able to bring back gravity. So to bring back gravity, all we had to do was to essentially take an action, and we're going to do in 4 dimensions, and we have to take the determinant of the metric. The metric in flat space is just -1, 1, 1, 1. So if you take the determinant of that, you actually just get -1. So it's actually not too complicated. But yeah, so you multiply -1, you put it in there, and you get 1. You get a negative sign there. You take the square root of 1, you get 1. So this is just 1 right here for now. But of course, if you had a more complex metric, then this would no longer be 1. It would be some really weird curved metric. And this is essentially how you could start to add gravity back into the action here. And you have the Lagrangian of the standard model, which now this should look very familiar. Should look very familiar. We have our gluons, we have our W's, we have our B's. These are just these are the gauges that we built from the helix strands. 1, 2, 3. The fermions are the loops that get closed. You kind of see it being like a little loop. Here's the left side of the loop, the right side, and it's just enclosing this little loop right there. And you get the Higgs and the Yukawa, but we won't worry too much about that right now. Let's go back to this and realize that if we wanted to try to calculate this, it looks cool. It looks nice. But the problem is that there are infinities that happen. If you go from, you do the real integral here, you usually have to go from 0 to infinity through momentum space. Let's see about all that. If we go to 0 to infinity in momentum space, then we get this thing which diverges. We get k to the third that goes to infinity. We get k squared down here. So, infinity to the third over infinity squared is still infinity. That didn't go away. So that's a problem. So this is what happens when you try to jam gravity into our quantum fields. But let's say that we return to the helix closure idea and realize that we have to close these helices with a specific length. We're thinking about this 2 pi, but like it's longer than 2 pi because you've twisted in time as well. So uh, there's a little bit of a helical twist to this. So you have a helix length cutoff, and this is built in to the system. It's necessary. It's unavoidable from the closure. Heisenberg's principle says that we should take position times momentum and give it some restriction, h bar over 2. And if we were to do that, we can consider, k is 2 pi over lambda. So we could say that sort of there's a momentum cutoff due to the length of the helix that we're using. So the length of this helix gives it a specific momentum cutoff. And because of that, and here we're going to make it invariant by sort of pointing and making sure that it works. And it seems to remind me a little bit of this Planck length here, because if we start to really look at it, kind of need a squared value here. So LP has a square root in it already. It really helps. So it could just be that LH is actually just the Planck length itself, and it kind of makes sense. We're taking 3 light rays. These helices are just light rays, and we're twisting them up around the circle. We're giving it that h over. There's a 2 pi in here, by the way. Right? H bar is actually just h over 2 pi. So it absolutely makes sense why the Planck length is what it is, because we had to take an h and we had to twist it around our circle in 3 dimensions. And we have 2 pi on the bottom here. We have our light ray going in 3 dimensions. And so we kind of need the Planck length to define our helix loop. We need it to be in 3 dimensions because if we just did it in 1 dimension, it wouldn't be the maximum. So the c to the third would be the maximum. Uh, but anyway, so there we go. Makes sense why we want the Planck length to be that way. But what's more important is that if we use the Planck length, or rather the Planck momentum, as our cutoff for our integral, it naturally renormalizes the infinity of of the integral that we're trying to solve. And so therefore, we no longer have this infinity. So it's less than infinity for any actual um, length of the helix. Since those helixes are required to build the standard model this way, and since the Heisenberg principle says that we should be taking momentum and position carefully in consideration, that they don't just go to infinity. Um, well, maybe they do, maybe they don't, but it's just kind of, this is all theory, I suppose. That's the cool thing, though. It makes a lot of sense, and it makes things very trivial and somewhat easy. So hopefully this made a little bit of sense, was able to help to derive the standard model just from space-time coordinates, and we split them apart, we factored them, we took linear factors, and then we square root them, and then we built all of the fields and the particles by twisting up those helixes. Um, yeah, this is some pretty crazy stuff. But anyway, hopefully this is interesting. Y'all have an awesome night. Thanks for watching.